Okay, so I'll let you stop reading. Today we're going to talk about 3 different things. Precision. When is something measured more precisely than another? How is it? Accuracy. When is something measured more accurately than something? They don't mean the same thing. Precision and accuracy do not mean the same thing. They're related. They sound like they should be. And then the other thing we're going to talk about is a range of tolerance. You know, sometimes we can talk about that we want something to be a specific value, but it's okay if it varies from that by a little bit, and there's a range of tolerance for what it is. Okay, just a second. Okay, go back to reading that box for me. Okay, here we are again. So when we're talking about, we have precision, accuracy, and range of tolerance to deal with today. The first thing we're going to talk about is precision. Precision is when you've measured something, the measurement that is most precise is the one that has been measured to the smallest unit of measure. So, if something is measured in ounces and something else is measured in pounds, which one is the smaller unit of measure, ounces or pounds? Ounces are, aren't they? Ounces are smaller than pounds, so we would say if they're measured to the nearest whole ounce versus measured to the nearest whole pound, we would say the ones measured to the nearest ounce are more precisely measured, okay? So, but sometimes we also have to look at, they're not both measured to the same unit, to like maybe like whole or tenth or hundredth or something like that. So we have to kind of look at it in a variety of ways. So let's look at this first one here. Choose the most precise measurement in each pair. We have 73.71 centimeters, which is 73 and 71 what? What are those? No, when it's 0.71, that's 71 what? Hundredths. So that's 73.71 centimeters is measured to the nearest hundredth, and it needs that TH there, not hundredth. So that 73.71 centimeters is being measured to the nearest hundredth, whereas the other one, the 736.2 centimeters, is being measured to the nearest what? Tenth. Okay, so then, because they were both measured as centimeters, we don't have to do any converting. We can just leave them and say, okay, well, they're both measured in centimeters, but which one's measured to the smaller unit of measure of centimeters? Is tenths smaller or hundredths smaller? Hundredths is smaller than tenths. Pennies are smaller than dimes. So hundredths is smaller, so this is the smaller unit of measure. So I want you to put that so we know how did we make the decision which one is more precisely measured. So the hundredths is the smaller unit of measure. They were both measured in centimeters, so we go with the fact that the 73.71 is to the hundredths, so we would say that the 73.71, the 73 and 71 centimeters is more precise then. It's taken out to the hundredths place, the other one's only taken out to the tenths. So precision means which one's measured to the smallest unit of measure. Okay, anybody have questions about that one? What's different in number 2 between our 2 measures? One's measured in milliliters and the other one's measured in liters. So just looking at it that way, which of those is smaller, milliliters or liters? Milliliters are a smaller unit of measure, but we can't, unless they're both measured to the same place value, we can't say, okay, well then it's going to be the milliliters one. Because the milliliters is measured to the nearest whole. It's to the ones place. The liters are measured to the hundredths place. So they're not measured to the same place value. So if they're different, if they're measured in different types of measure, milliliters versus liters, and they're measured to a different place value, we have to do more work than we would otherwise. Okay, so what we're gonna do is we're gonna take that 4,732 milliliters and we're gonna change that into liters. Okay, so how many, so we need to do a conversion problem here. 4,732 milliliters over 1. Remember we did this before. And we need milliliters downstairs because we want them to go away. We need liters upstairs because we want to change our milliliters into liters. Anybody happen to know the conversion factor for milliliters and liters? Milla.
It's
1,000.
1,000 milliliters per 1 liter.
Yeah, it's 1,000 milliliters per 1 liter. So again, just like we did when we were doing this back earlier, the milliliters now cancel out. We're going to have our liters like we want. So now we're just going to say, okay, I got to do 4,732, because that's times 1 upstairs, divided by 1,000. What is 4,732 divided by 1,000? 4.732, yeah. Whenever you're dividing by powers of 10, you can just move the decimal point back as many zeros as there are. So there are 3 zeros in 1,000, so we can just move it back 3 places. Okay, so now we have it converted into liters. So now we're going to compare, these two are now going to get compared to each other. We got to see which of those two are measured more precisely. So what's this one measured to? Oh, what place value is the 4.732 measured out to? Cameron? To the thousandth of a liter. 1,000 with a TH at the end. So after we converted it, it's shown that it's taken out to the thousandth of a liter. And the 4.73 liters, which we didn't have to convert, that one was liters. What's that measured to? What place value is that one measured to? Hundredths. Hundred with a TH behind it. Hundredth of a liter. So, now that we're comparing liters to liters, which one's measured out to a smaller unit of measure?
4.73.
The 4.73. This is the one that is the smaller unit of measure. So we're going to say then that okay, but remember, this right here, this is the one that we're saying is smaller, but what was it to start with? It was this. It was the 4,732 milliliters. That's what it was to start with. We converted it so we could make the comparison. These two are the same. So we figured out that this one, after we converted it, we still can agree that it's going to be the one that's more precise because it's a smaller unit of measure. Okay, so keep this in mind. If they're measured to the same thing, centimeters to centimeters, inches to inches, hours to hours, if the measure that they're measured in is the same, then you can just compare which one's measured out to the smallest unit of measure, which one's taken out to the smallest place value. You can compare them that way. But if they're not, then you look at them and you say, okay, well, if we got hours being compared to minutes, let's say, we have hours being compared to minutes, but they're both measured to the nearest whole. So you're measured to the nearest whole hour, you're measured to the nearest whole minute. They don't vary in their place values. If they're measured to the same, then you can say, well, minutes are smaller than hours. So minutes would be the more precise measure. But if they're like this one was, they're both different, milliliters and liters, and they're not measured to the same place value. The first one was measured to the ones place, the second one was measured to the hundredths place, then we have to do a conversion so we can compare them. So you're going to have to do some critical thinking here too. You can't always just say whatever the smallest thing is, minutes, hours, that's going to be the answer, is going to be minutes, hours. You have to be able to make a comparison correctly. Cameron?
What if it's the same place value, the same thing, but
place values, then you would say that one is not more precise than the other. You'd say neither. Sometimes you can say neither, is they're both measured as, one is measured as precisely as the other. So if one was measured to 23 minutes and another one was measured to 45 minutes, we would say neither of them is more precise because they were both measured to the nearest minute. Whole minute, okay? Is that what you meant? Okay. So we can also have, which is a good point, Cameron, you can also have, one is not more precise than the other. It can be a neither. Okay, now let's talk about we're going to practice some more precision in this problem, but we're going to introduce what is accuracy then. How is accuracy different? So it says here, the accuracy of a measurement is the closeness of the measured value to the actual value, what they really want it to be. So if you say you want a 1 pound chunk of fudge, and you're going to get charged for 1 pound of fudge, you want to get it as close to 1 pound as possible, right? You want them to be accurate, don't you? You don't want to be shortchanged on your fudge. So in this case, we have a 45-pound object that is weighed on 3 different scales. That's a big piece of fudge. The results are shown in the table. So scale 1 measured this 45-pound object. It's measuring to the nearest what? What's that one measured to? 1/10 of a pound. First, we're going to deal with precision here, okay? So that one's measured to the nearest 1/10 of a pound. Scale 2 is measuring it to the what? 100th? Thousandth of a pound. Notice they're all being measured in pounds, aren't they? We didn't have to do any converting here. We get to just compare which one's measured, what they're measured to. What's scale 3 measuring it to? To the nearest 100th of a pound. So which scale measured this most precisely?
2.
Scale 2. Why scale 2?
Because it's the smallest.
Yeah, because it's the smallest unit of, I did that. Because it is the smallest unit of measure, isn't it? So you have to make the decision when they're measured in the same, once they're measured in the same thing, which one is measured out to the smallest unit. Thousandths is smaller than hundredths, is smaller than tenths. It's not.
We have homework today.
Yes, we do. Okay, now let's talk about accuracy. How are we going to find which one's most accurate? Because scale 2 doesn't have to be considered the most accurate. We are going to do accuracy by saying, okay, which one is the closest to what it was supposed to be. So I want you to put accuracy down like this. And I want you to, what we're going to do is we're going to do some subtraction problems to see which one is closest to it. So we have a 45-pound object, scale 1. Let's start with scale 1. 45 is bigger than 44.9, so we will subtract. Biggest one, take away the smaller. What's 45 take away 44.9? How close is that one? 0.1. It's a 1/10 of a pound away. Oh, I'm sorry. So it's a 44.9 being taken away from 45. It's a 1/10 of a pound away. They measured it a 1/10 of a pound away. Scale 2. Okay, 45.105 is bigger, so this time we're going to have to start with that one because it's the bigger one and take away the 45, what we want it to be. So what's 45.105? Take away 45. 0.105. Okay. And scale 3. So now that one's 105 thousandths of a pound away. Okay, what's scale 3? Is 45.01 over or under 45? Over, so we'll start with that one. Take away the 45 that we want it to be. What's the difference between 45.01 and 45? 0.01. Okay, so here's what I want us to do. Let's make all of those into thousands by putting zeros behind them. So the ones that need them. So we're going to put two zeros behind that one, make it into thousands. This one's already thousands, and we're going to make that into thousands.
3.
Which of those is the least amount of distance?
3.
10 thousandths, 100 thousandths, or 105 thousandths? The 10 thousandths, isn't it? That's the one that's closest to it. It's only 10 thousandths of a pound away. So scale 3 gets to be the one that's most accurate. Scale 2 is most precise because it measured it out to the smallest unit of measure. Scale 3 is the most accurate because it measured it the closest. Any questions about understanding the difference between finding the most precise measure versus the most accurate measure?
Can I have your attention? Please excuse all dual credit math students to Mr. Starr's room at this time. That's all dual credit math students to Mr. Starr's room.
Rose?
For scale 3, are we like is it accurate because it's measured to the most? I mean, to the nearest whole?
No, it's not because it's to the nearest whole number. The reason is because on the number line, it would be the one that is closest to 45. So it's only 10 thousandths of a pound away. This one's 100 thousandths of a pound away. Isn't that further away? And 105 thousandths away, that's even further away, isn't it? So we want the one that's closest. Okay? Okay, let's go see what we're doing on the back. Now we're doing our other topic for today, which is tolerance. Tolerance describes the amount by which a measurement is permitted to vary from a specific value. And it's often expressed as a range of values. So, first one we're going to deal with is what if they give it to us as a percent? What do we have to actually do? Okay, so they want it to be 50 in this one. It's 50 kilograms plus or minus 2%. We want to know what are the numbers it can go to. We don't add 2 and subtract 2 because that's 2%. We want 2% of 50. So the first thing we have to do is we have to find out what is 2% of 50. So they took the 50 and multiplied it by 2%, changed to a decimal, and found out that it can vary by 1 unit, 1 kilogram. So then the next thing that we have to do is we have to add and subtract that. So we say 50 plus 1, that gives us the 51. 50 take away 1, that gives us the 49. So the range for that one became 49 kilograms to 51 kilograms. Okay? So that was our example one that was already done for us. Now we're going to do a couple of them. Write the possible range of each measurement, round to the nearest tenth if necessary.
Can you go back?
Sure. So, what's our first move have to be? Step 1, what do? We multiply to find out how much it can vary by. So we're going to change 4% to a decimal. And what is a decimal for 4%? 0.04, not 0.4. 0.04. And now we're going to multiply. We're going to do 50 times that 0.04. 50 is what they want it to be. So, what is 50 times 0.04? 2. What's that 2 tell us?
It can vary by 2.
That's how much it can vary by. How much it can vary by. That's what we just found right here. How much it can vary by. But we're instructed to write the range. So what do we have to do? Next thing we have to do then is basically what we've just found is that instead of it being 50 kilograms plus or minus 4%, it's 50 kilograms plus or minus 2 kilograms. That's what we just changed it to. So we know that that 4% is actually 2 kilograms. So now what we're going to do is we're going to do our adding and our subtracting. So that's what this says. 50 kilograms plus 2 kilograms, 50 kilograms minus 2 kilograms. It's kind of like a shortcut way of being able to write it together instead of having to write it twice. So 50 take away or add to is what? 52. 50 take away 2 is 48. So 50 is in the middle, but they're willing to let it go down to 48. They're willing to let it go up to 52, whatever this is. So we say our range, this is our final answer here, our range. So that was doing all of our work. What's our range then? 48 kilograms to 52 kilograms. There you go. This is what they were asking us for. Emerson. We do want the smallest one at the left end and the larger at the right end, yes. Jason.
So like on the percent, we just do half of that. So like for 2 we did 1, 4 we did 2. And
No, it just so happened that it turned out to be 1 and 2, but the half of the thing, be careful about that. You just always have to calculate what it's going to be. Okay, like the next one here is we start out with a different number, and then we also use a different percent. So let's see what happens in this next one. So first thing we have to do is we have to say what is 1.5% as a decimal. Here's what I'm going to recommend you do. Write it down without the percent sign. And the shortcut is move the decimal point back 2 places. So you're going to go like this. Here's your new decimal point. You're going to put a 0 there. And it is 0.015. That's the decimal name for 1.5%. Okay, after we find out what the decimal is as a percent, what's our next move?
Multiply
Multiply,
125.
take what we want it to be. 125 has to get multiplied by that 0.1015 that we just found out what the percentage is of 125. Or we're going to be finding out what 1.5% of 125 is, I'm sorry. And we're going to do it by multiplying it with its decimal form. And it said up in our directions it needs to be rounded to the nearest tenth. Does this one need to be rounded? What's it come up to?
1.875.
1.875. Is this tenths?
No.
Is that 875 tenths?
No, that's thousand.
That's thousands. So we're going to take that and we're going to round that to 1 point what? 9. Okay. And now what are we going to do with that 1.9?
Add a 0.
Add and subtract.
Yeah, we're going to add it and subtract it to our 125. This is how we write it first. We say 125 plus or minus 1.9, which means then that we have to add it. See what we get. We have to subtract it. See what we get. So when you add it, you should get the high end of the range. When you subtract it, you should get the low end of the range. So what's the high end of our range? Okay, 126.9. What's the low end of our range? 123.1. we done? No, we have to write the range with the labels, right? Okay, so this is 125 pounds of something. 125 pounds of something that can vary by, that isn't what I wanted to do, sorry, erase that, I was totally off. We're showing the range now. So, the low end is 123.1, and those are what?
It's,
Pounds to
to 126 point.
the high end, which is 126.9 pounds. And we want labels in there so we can show what this stuff is measured in.
Wouldn't the low end be 124.1 instead of 123.1?
No. If you just took away 0.9, it'd be 124.1, but we took away 1.9. So, Jason was right on that. Okay, any other concerns? Questions? Need me to go back to anything?
So, is that